All right. So we left off, we were looking at this problem that deals with the chlorination of methane. So this question specifically deals with the chlorination of chloroform. So what it's saying is if you're, so chloroform, chloroform is this molecule, CHCl3. So if we treat that with chlorine, we should end up with carbon tetrachloride, CCl4, and HCl, okay? So that's the reaction. And when we sum our propagation steps, right, that should be the overall reaction that we get. We're going to start it with the initiation, which is going to be the formation of a radical. So for that, we're going to start with our chlorine. And instead of drawing in every lone pair, I like to draw my radicals like this sometimes. Don't put any unpaired electron, or don't put any of the lone pairs. And then just draw my two fishhooks and leave out, I mean, you could leave out all the electrons, but then just put them back in and just say, I'm going to get two chlorine radicals. So one chlorine radical and two chlorine radicals like that. If you wrote two Cl radicals, like if you just put a 2 here, like that, that's totally fine as well. Okay, but that's our initiation. So now we're going to do our propagation steps. So propagation, and I'm writing small for me because I don't want to run out of space here. So the first part of propagation is going to be hydrogen abstraction, and the second part is going to be halogen abstraction. So for our hydrogen abstraction, we're going to draw the chloroform molecule like this, and then it's going to combine with a chlorine radical. Excuse me. And we're going to abstract that hydrogen. So remember, we're going to end up forming HCl. So we're going to form the CCl3 radical. We've got the CCl3 radical. Plus, we also form some HCl gas. Okay, so that's the hydrogen abstraction. The next part is going to be the halogen abstraction. So you can put here X abstraction. I'm going to put Cl abstraction since that's the halogen that we're dealing with here. So now my CCl3 radical, okay, that's going to combine with chlorine, right? And it's going to abstract a halogen from chlorine or chlorine gas. And remember, when you shine the light on the chlorine, okay, and I didn't even put light in here, and you could put heat if you wanted to. Remember, you only form a few chlorine radicals. So you have lots of chlorine gas still in your reaction mixture. So now we're going to form our another carbon-chlorine bond. And so what that's going to look like is this. So we're going to have CCl4. I'm not going to, well, I'll draw the whole Lewis structure like this. And then, of course, we're also going to end up forming a chlorine radical like that. So, of course, if you tally up those two steps, okay, you can see that you're going to cancel out the chlorine radical would be canceled out. And you're also going to cancel out the CCl3 radical. And so overall, you end up with exactly what you have in blue at the top. You end up with CHCl3 plus Cl2 gives you CCl4 plus HCl, right? The propagation step should always tally to give you, excuse me, the overall reaction. So now we're going to draw the termination, and I don't care what two radicals you draw. I'm going to make it as simple as I possibly can. So I'm going to put two chlorine radicals, meet on the street like this, and they form a chlorine-chlorine bond. And so we end up with chlorine, okay? And I'll put in my lone pairs at the end. So there's your termination. So that's the entire mechanism. It's kind of lengthy, but it does show you the initiation, propagation, and termination. And again, just as a reminder, the two propagation steps, they should tally up to give you the overall reaction, right? The same reaction that we saw up here. All right, so with that in mind, the last part of section 10.3 deals with what are called radical initiators and radical inhibitors. So if you're wondering, you know, how do I make a radical besides heating up chlorine? Because actually it takes quite a bit of energy to do that. You can see that it takes 243 kilojoules per mole to break a chlorine molecule. But if you want something that's going to cost you a little less energy to break apart, you can use a peroxide. And an alkyl peroxide, you can see it takes a significant less amount of energy. And an acyl peroxide takes even less energy than that. So if you're like, well, this kind of looks familiar to me, back in the alkenes chapter, we talked about HBr and ROOR, right, and alkyl peroxide. And it is the same alkyl peroxide. And actually, we're going to talk about this reaction towards the end of the chapter. And we're going to get into the whole rationale of anti-Markovnikov addition. Anyhow, so it says here, which initiator above initiates reactions most readily? Well, the answer is going to be the acyl peroxide, right? The answer will be acyl peroxides, okay? Since weakest bond. And you can imagine why that is, because you end up with something that is resonance stabilized in the end, right? You could draw a resonance contributor for this. Anyhow, so there you go. So we can use an acyl peroxide, we can use an alkyl peroxide, and we're actually going to use those. And then a dihalide, yes, you can use it, but it just takes a lot of energy to do that. All right, so let's just talk about inhibitors here just for a second. And the thing about radicals is that sometimes we want to avoid having radicals in a reaction mixture. Like if you remember back in General Chemistry 1, you would have gone over why the Lewis structure of oxygen actually shows that it's a diradical, because it actually has some magnetic properties, and I'm not going to get into all of that right now. But if we want to eliminate a radical like oxygen from a reaction mixture, what we can do is we put in a radical inhibitor. And again, because radical reactions, if you form a radical and you have oxygen in the reaction mixture, it can react with the radical, and it basically ruins everything. And so to scavenge or to destroy the oxygen, what you would do is use a radical inhibitor. And hydroquinone is a commonly used scavenger of oxygen radicals. Why? Because it can actually react with two radicals. And the mechanism is shown down here, or just the overall reaction is that it can abstract, or let's say you have a radical in your reaction mixture, it can abstract the hydrogen to get this resonance stabilized radical here, and then it can do it again, and you end up forming this molecule here called benzoquinone. And so it's very easy to just put some hydroquinone. It's a very inexpensive reagent. Just put it in your reaction mixture, and therefore it can avoid having any unwanted radicals in your reaction mixture and prevent, your reaction from being slowed down. I mean, our book doesn't go into a whole lot of details as to how this happens. Radical reactions very slow in the presence of oxygen, and I'm not going to go into a whole lot of detail about it either. But this is one of the questions I was asked during my defense when I was defending my thesis in graduate school. They asked me some questions about radicals and how to avoid them, because I had done many reactions where I tried to get rid of oxygen from the reaction mixture, and it wasn't always easy to do. Anyhow, let's turn our attention to section 10.4. All right, so take a deep breath, stretch maybe for a second, because section 10.4 and 10.5 are going to be very important to your understanding as to why we use bromination a lot more than we do chlorination in chemistry 3101 and 3111. And again, you might look at it and say, well, really, it takes 2 sections to cover this? Yeah, it kind of does, okay? So just bear with me. And what we're going to look at in the next 2 sections really is we're going to look at, well, come on, Mr. Dion, there's 4 halogens, aren't there? Right? Why don't we do halogenation with fluorine? Right? Why do we only do chlorination and bromination? These are the ones that we're going to use, and we don't do iodination. Well, again, there's very good reasons why we use mostly chlorination and bromination. And out of those 2, we use bromination the vast majority of the time. Very, very good reason for that, but it takes us almost 2 sections to get through it, okay? So first of all, if we want to know if a reaction's even going to work, we have to look at delta G for the overall reaction, right? We always have to take a look at delta G. And if our delta G is negative, then we know the reaction is spontaneous. Well, when we talk about a halogenation reaction, we can kind of ignore the entropy term, right? We can kind of cross this term off. And if you're wondering, well, how can you do that? Well, the reason why is because if you look at the change in entropy, okay, you're starting it with 2 molecules, right? And then you end up with 2 molecules. So it's kind of like your delta S is close to 0. And so if this number is 0, then it cancels out the T. And then what you end up with is a very abridged version of the delta G equation, which is delta G is pretty much equal to the change in enthalpy for your reaction, okay? And that's a good thing because it makes it a lot simpler. We don't have to calculate the T delta S and all that stuff. We can just look at bond association energies and make the comparison between change in enthalpy and say it's pretty close to the change in Gibbs free energy and make an assumption as to whether the reaction is going to work or not. And so if you look at the halogenation of methane, whether it's done with fluorine, so this is done with fluorine, F2, Cl2, Br2, or I2, I have all the bond association energies here in this table, 10.1. So of course, the bond association energies for the carbon-hydrogen bond, that never changes. Then you have the 4 halogens here. Then you have the bond association energy of the new carbon-halogen bond. Then you have the new HX bond that's formed. So I'm not going to do the math for every single one of these, but you can imagine, I suppose you could if you wanted to, right? If we just got a little practice here, we said the delta H for fluorination. We'll do fluorination like that. Remember, it's bonds broken minus bonds formed. So we take, we'll put bond association energy broken minus bond association energy formed. Now, I did this ahead of time, so I'm not going to go into all the math here. But if we're just doing fluorination, so just this one here, we would say 435 plus 159. And then, of course, we're going to subtract all of this, which would be 456. And this is all kilojoules per mole plus 569. Like that. And, of course, everything is in kilojoules per mole. And you end up with a delta H, which is equal to, I got negative 431 kilojoules per mole. Well, if you looked ahead in the slides, you probably noticed this number was already shown in the slides. So you can see that for fluorination, if delta H, if this is close to being equal to delta G, right, the number is negative. So fluorination is definitely a spontaneous process. So let's take a look at the delta H's for all of these. So this is the one that I just calculated on the previous slide. You do the same thing for all the others. And what do you notice? Again, if delta G is pretty much equal to delta H, you notice that all three of fluorination, chlorination, and bromination, these are all spontaneous. They all work. All right, but you notice something about fluorination? Ooh, fluorination, the delta G is going to be a positive number. So iodination is actually not a spontaneous process. So there's the answer to the first one. Why don't we do iodination? It's not spontaneous. Now, fluorination is spontaneous, but the reason we don't do it, can anybody guess that as to why we don't do fluorination? Can anybody guess as to why? Yeah, thanks, Sarah. Absolutely. So Sarah says it's too exothermic, right? It's too reactive, right? So we'll put here too reactive. Right, Sarah? And when we have something that's too reactive in organic chemistry, that could lead to an explosion. And so chemists generally frown on, having explosions in the lab. Sounds like fun, but it's not, okay? So again, all three of these, fluorination, chlorination, and bromination, remember, they're all spontaneous. The delta G is negative for all of them, but fluorination, it's not really useful. If you remember back in general chemistry too, fluorine is the strongest oxidant, so it can be dangerous. And again, the iodination is it's too slow. It's non-spontaneous, so it's not really useless or useful for us. It's useless for us. But again, I told you that these two are going to be the ones that we're going to focus on anyway. Are going to be chlorination and bromination. So based off of that, our conclusion: fluorination too violent, iodination endothermic, so not thermodynamically favored. And so halogenation with chlorine and bromine, those are the ones that are going to be useful. And now we're going to take some time and we're going to delve into the reason why. It turns out that bromination, as I keep repeating to you, bromination is actually more useful depending on your starting material. All right. So let's see here. Okay. If we examine both of the propagation steps, so these two steps here, these are the propagation steps for the chlorination and the bromination of ethane, right? This is an ethane molecule here. This is the first propagation step. This is the second propagation step, right? So the first one is hydrogen abstraction. The second one is halogen abstraction. And all they're doing is evaluating what's the change in delta H for each one of the steps, okay? So if you look at the delta H for the hydrogen abstraction, for the chlorination and the bromination, you notice that for the chlorination, it's exothermic. So you see here, this is exothermic, but you notice that for bromine, it's endothermic. Okay, so you might look at that and say, well, if the first step is endothermic for bromination, that must make it less useful. But in fact, this is what makes bromination so useful, and I'll explain that in just a second. And if you look at the change in enthalpy for the halogen abstraction for both of them, they're pretty much identical. Okay, they're pretty close, -96, -92. So if you tally up the numbers for both of the propagation steps for chlorination, you get negative overall, so that's good. That means it's going to be spontaneous. And if you tally up the delta H for both of the steps of bromination, well, you can see the second step, the release of energy is greater than the energy required for the first step. And so overall, it is a delta G negative process. And so bromination is going to be a spontaneous process, even though the first step is endothermic. But what we're going to take advantage of is the fact that that first step is endothermic. So now, what we're going to do is we're going to look at both of these steps, all right, on a reaction coordinate diagram. So here's the chlorination. Remember, the chlorination, the first step, which would be this part here, the first step is going to be exothermic, right? You see the products are more stable than the reactants. You also see that the second step is exothermic, right? You see the products are more stable than the reactants, okay? So no big surprise there. And if you look at the second step of bromination, yes, products are definitely more stable than the reactants or the intermediates, you know, here. So what's of interest to us in this slide really is going to be mainly this step here. The fact that the hydrogen abstraction for bromination is an endothermic process, right? You can see that the energy of the radical is a lot greater than the starting material. So the fact that it's got this huge activation energy makes the bromination more selective, okay? And if it's more selective, it's going to be more, we're going to put here, more useful to an organic chemist, all right? More useful for us, okay? So now what we're going to do is we're going to delve into the first step only. Really, we're just going to examine, so I'll put a box around this step in green, and then if we put a green box around this one too, we're really going to focus in on the hydrogen abstraction step. Okay, so again, the first part is the hydrogen abstraction. The second half of the curve is the halogen abstraction. And you notice that the hydrogen abstraction, or what's in the green box for both of these, is the rate determining step. So that's also going to be interesting to us. Now, here's a really cool experiment. Okay, so now we're moving into section 10.5. Like, I'm trying to do it seamlessly here. Okay, so now we're really going to focus in on why bromination is more regioselective. And obviously, it's got something to do with that first step, right? So it says, if you have a substrate that's more complex than ethane, right? Because in ethane, there was no differentiation. All of the hydrogens are chemically equivalent, if I can use that term again. So there's no differentiation between any of the products that you would get from halogenation or from bromination or chlorination. But if you look at propane, so this is a molecule of propane here. Now propane has two different types of hydrogens. The ones that you have highlighted in orange, if you were to abstract one of those, you'd get a secondary radical. And the ones in green, if you were to abstract one of those, you'd get a primary radical. So these are different, the hydrogens have different reactivities. They're different bond association energies. So what happens is if you try and chlorinate propane, you get two products. You get 2 chloropropane, okay, and you get 1 chloropropane. Well, it actually turns out that the 2 chloropropane is formed in a greater amount. Let's take a look, okay? When you chlorinate propane, you actually form 2 chloropropane 60% of the time, and 1 chloropropane is only 40% of the time. That doesn't make any sense when you think about it at first, right? Because the ratio should be 3 to 1, right? It should be 3 to 1 for this because there's 6 protons here and there's only 2 protons here. But again, we not only reverse the ratio, but we get more, we get more chlorination at the middle carbon than we do at either the terminal carbons. And you can see that that the rationale is shown down here. It's all based on that first step, the hydrogen abstraction. So now what we're doing is we're looking at, again, where are we? Let me just back up to show you. We're looking at this curve right now, but now what we're doing is we're going to compare it for a primary, and then we're going to look at a secondary, et cetera, and a tertiary. So let's go back here and let's take a look. And you can see that the activation energy, whether you form a primary radical, that's the line in red, or a secondary radical, that's the line in blue, the difference in activation energy, it's not all that great. There is a difference in activation energy, but it's not huge. And then if you look at the stability of the radical, you can see the secondary radical is definitely more stable than the primary. But the activation energy for the formation of the secondary radical is lower, right? This activation energy is lower than the one to get up to this position right here. And so we've got two explanations as to why chlorination at this carbon is going to be preferred. Number one, the activation energy is lower. And number two, you form a more stable intermediate. The radical that's formed is going to be more stable. Give me a thumbs up if you're with me on this so far. Even if you're with me 60% of the way, that would be good enough for now. So now let me show you another cool experiment, okay? We're going to do this same experiment, but we're going to replace the chlorine with bromine. Check this out. If you do the reaction with bromine, okay, so we do a bromination. Yeah, the reaction is slower, but look at the ratio. We almost get exclusively the 2-bromopropane, and we get only very small amounts, 3% of the 1-bromopropane. So we say that the bromination is more regioselective, right? It's more selective for one region over another, and we can explain that using the Hammond postulate. So remember the Hammond postulate, it brings together the idea of whether a reaction is endothermic or exothermic, and it relates that to the transition state. So let's take a look here. So now what we're doing is we're comparing the hydrogen abstraction step, okay? So this is hydrogen abstraction, as is this, but this is the hydrogen abstraction for chlorination, and this is the hydrogen abstraction for bromination. So remember, hydrogen abstraction for chlorination was exothermic, right? Hydrogen abstraction for bromination was endothermic. So this is really the key, the fact that this reaction is endothermic. So let's get into it here. All right. Now, if we focus in on just this step alone for the chlorination and the bromination, you see that the transition state will be more like the reactants or more like the products, depending on whichever it's closer in energy to. So if we look at chlorination, okay, I'll use my black pen here. You see that for chlorination, the transition state is much closer in energy to the reactants. So that means that, remember, we're forming a radical here is the intermediate, right? The intermediate is a radical in both reactions. So that means that the transition state in the chlorination, what I'm looking at right here, it has very little radical character. It looks mostly like the reactant. It hasn't changed very much. Now, if we look at the bromination, you can see that the transition state is a lot closer in energy to the radical. So that means when you reach the transition state, it looks a hell of a lot like a radical. Well, we know that a radical that is secondary is going to be more stable than a radical that is primary. So that is why the bromination is going to be more selective, because your transition state is going to more closely resemble a radical. The transition state for chlorination, it doesn't look like a radical much at all. So if you want to see a picture of what I'm trying to describe to you, is that when you're at the transition state, okay, this is what it looks like for chlorination. The carbon-hydrogen bond is only beginning to break. Yes, the carbon has a little bit of partial, radical character, but not much. If you look at the bromination, on the other hand, the transition state looks a heck of a lot like a radical. Why? Because this bond, the carbon-hydrogen bond, is mostly broken. And so that is why it's going to be more selective, right? If the transition state looks a lot more like a radical, we know that a secondary radical is more stable than a primary, or a tertiary radical is more stable than both of those. Whereas with the chlorination, it doesn't really look like a radical anyway. So there's going to be very little differentiation between the two. And so that is exactly what I'm explaining here on this slide. For bromination, the stability of the transition state largely depends on the stability of the radical that's being formed. Whereas in chlorination, the stability of the transition state, it doesn't really rely on the stability of the radical that you're making. It doesn't really matter a whole heck of a lot because the bond has only begun to break. Now, if you're like, can you show me on a reaction coordinate diagram? Sure. Again, we're only focusing on the first step, my friends. This is the first step, the hydrogen abstraction for chlorination. But you see the difference in energy as to whether you're doing or forming a primary, secondary, or tertiary radical. There's only very little difference in the transition states or their energies because it's not really got much radical character anyway. Sure, a tertiary radical is more stable. Yeah, we get that. But there's very little difference in energy between these transition states. Whereas if you look at the bromination, whoa, baby, okay? It's the same step, but you can see that there's a huge difference in energy between the transition states. Sure, the energy difference between the radicals doesn't change. That's the same, but the energy difference in the transition states is huge. And so the activation energy to form the tertiary radical is going to be much lower than the others, and that is why radical bromination is so much more regioselective. Give me a thumbs up if you're with me, even 65% of the way with me. You will have to read this. I would say it's a good idea to read this maybe once or twice, but as long as you follow me on the rationale here, you're gonna be sitting pretty. So let me just find where I am here in my notes. And so, you know, if I only had 60 seconds to lecture to you what I've just been explaining for the past quite a while, okay? Here's what I would have showed you. Here's what I would have shown you is this. I just would have said, look, you guys, if you have this compound, you can see there's two types of protons. You have these protons here that I'll put in blue, and then you have these protons here that I'll put in red, okay? If you do a chlorination, there's very little discrimination between whether the chlorination occurs at the blue position or the red position. But if you do bromination, man, it's going to be super selective. Why? Why is it almost only going to pull off the blue proton? Because remember, the transition state is going to closely resemble this, and a tertiary radical is a heck of a lot more stable than a primary radical. Give me a thumbs up if you follow me on this slide. Again, I think it's very important. So can we do a chlorination? Yeah, sure, you can do chlorination. There's, don't think that I'm a bully towards chlorination and Mr. Dion hates chlorination or anything like that. There are times when chlorination can be fine. Let me show you an example, okay? I'll just zoom in here and just show you a quick example. What if you wanted to halogenate cyclohexane? There's no differentiation between any of the protons in here. Everything is just a CH2, right? Everything's just a methylene. So in that case, sure, you can treat it with chlorine. That'll work, okay? And that's going to give you chlorocyclohexane plus HCl. But really, that's a really isolated case, right? As soon as you put a group on there, like let's say you have a methyl group, then chlorination is not going to be very useful, okay? And again, we're going to see some examples of that as we move forward. Now, this next slide here is just kind of showing you how, yeah, fluorination does work, right? There's, again, there's nothing wrong with fluorination, I guess, theoretically either, right? It is a delta G favored process, right? It is a spontaneous process, but you can see there's very little differentiation. And so if you have a molecule that's got primary, secondary, and tertiary positions, you're going to end up with just some mixture where it's split in three, and then you've got to purify it. The same thing with chlorination. If you have any kind of differentiation, if you have a primary and a secondary, you've got a big mixture. Whereas if you're doing bromination, if you have a tertiary, carbon-hydrogen bond in there, that's going to be your best bet because it's going to, mostly halogenate in that position. All right. So with that information in mind, let's take a look at this question. And I know you're going to nail this, but it just says, predict the major product that you get upon radical bromination of each of the following compounds. So all it's saying is if you were to take this compound and treat it with bromine and some HNu, some light, if I highlight this position in red, this position in blue, this position in green, I don't know, and this position in black or something like that, okay? Could anybody tell me where's the bromination going to occur? At which place? Which hydrogen is going to be abstracted? Exactly, it's the red one, right? Because that's going to give you the most stable radical. Exactly. So, You know what we could do is we could even draw the intermediate. It's not asking us to do that, but hey, it's the land of the free. So we could draw the radical that's formed as an intermediate, right? And then, of course, that's going to do the halogen abstraction. And so your final product is going to look a little something like this. Okay. Sorry if you can hear my kids crying upstairs, but my youngest is crying about something. Anyhow, so let's see here. We got bromine and light for the next one. Let's say I put this proton in blue. Let's say I put this proton, you can't see yellow. Let's say I put this proton in green, and I'll put this proton in red. I don't know. Sean, give me the answer, or anybody. Ashley, whoever's there. Who's got the answer? Where is it going to do the bromination? Yes, thanks, Kiana. Absolutely. It's going to be at the blue position, right? Because that's going to give you the most stable radical. There you go. Beautiful. Great. And again, we don't have to draw the intermediate, but, you know, it's just some food for thought. You know, that's the radical that's going to be formed as your intermediate. And then, of course, that's where your bromination is going to occur. So, oops, what am I doing? Mr. Dion, I think I need even more coffee, maybe. There we go. All right, give me a thumbs up if you're with me on that. Cha, I knew you would be. So if you're wondering, you know, where is all this going? Where it's going really is, you know that if you take a hindered base, you know, you could do an elimination and form an alkene, right? Like this. Or you know that if you if you took a non-hindered base, jeepers, you would end up with this, right? And then you've got chapter 8, all the different alkene chemistry that we studied, et cetera, et cetera. Anyhow, that's kind of where it's going, really. Anyhow, we'll get to that in a second. There's some other concepts that we have to cover. One is, hey, I have a question for you guys. This is a pop quiz. Who could tell me? So let's say I do, I take this molecule and I do the hydrogen abstraction. I'm going to form two radicals, aren't I? I'm going to form, let me draw it the way it's drawn on the page. I'm going to form this radical, and I'm also going to form this radical. Who remembers what the molecular geometry is of a radical, of a carbon radical? What's the molecular geometry? Not the hybridization. What's the molecular geometry? Trigonal planar. Heck yeah. Thank you. Savannah, good. It's trigonal planar, right? And then that intermediate is going to do the halogen abstraction, right? This one's going to do the halogen abstraction. All right. So we see that this is a chiral center, right? This center, the one that's highlighted in green, is a chiral center. And so if your intermediate is trigonal planar, there's going to be no differentiation between which side the chlorine is going to be attached to. And so if you end up forming a chiral center, and you can see that we do form a chiral center, you're going to end up with a racemic mixture. Does that make sense to everybody? And if you're rolling your eyes going, oh man, I got to remember the whole stereochemistry bit from chapter 5. Yeah, it never goes away, okay? Never goes away. All right, so as long as you understand that, and you kind of got to be on the lookout for a chiral center. So if you can form a chiral center, like one chiral center in a molecule, you get a racemic mixture. And get this, let's say you started it with something that's chiral, right? Let's say that, you know, you worked all week, you know, Sarah was slaving in the lab, working and trying to make this compound with this chiral center. And then she said, well, I'm going to do a bromination on it. You know, I'm going to brominate this guy. Well, this chiral center, this one here that you worked so hard to make, remember, as soon as you brominate that, you end up forming this intermediate. And you've destroyed, right? You destroy the chiral center. And so even if you worked so hard to make a chiral center, you destroy it, right? You end up you'd get a racemic mixture in this case. And if you're like, well, that stinks. Yeah, it does. It does stink. But sorry, there's nothing we can really do about it, okay? You'd get a racemic mixture of R and S in this case because you have a new chiral center, right? And there was another example I wanted to show you about diastereoselectivity, but maybe I'll show you that next class or something. Anyhow, let's get some more practice on this, and I'll test you with the same thing. on the first one, let's see here. If I draw maybe this hydrogen in red, if I put this one in blue, and then if I put this one in black, maybe, I don't know. Which one of those, where's the bromination going to occur? Where the blue one is, the red one, or the black one? And it's not a trick question or anything. Yeah, where the red one is, right? So remember, that's a chiral center, isn't it? This is a beautiful chiral center. So are you going to end up with one stereoisomer in the end? Heck no, not if you're doing bromination, okay? So let's see, if you treat this with bromine and light, let's draw the intermediate that's going to be formed. Remember, the radical is trigonal planar, right? It's trigonal planar. And so now, when you do the halogen abstraction, and we could even draw the mechanism if we wanted to, right? We could say bromine here, okay? So now when you do the halogen abstraction, like this, right? The halogen can come in from either face of the molecule. It doesn't discriminate whatsoever. Oops. Whatsoever. And you're going to end up with this. So you're going to end up with the destruction of your beautiful chiral center. Huge bummer, but so is such as life sometimes. Oh, this is an example I wanted to show you. Is this example down here at the bottom. Now, I know that you can all identify this position as being the only tertiary position in the molecule. So that's where your hydrogen abstraction would occur. So if you treat this as bromine, let's do heat for a change, okay? You end up with this intermediate, which you have a trigonal planar carbon here where the radical is, but you still have a chiral center over here. And this chiral center is completely untouched. So now you have a radical, but it does still have a chiral center in the molecule. And so there is going to be some selectivity as to which side the bromine adds to. You see, this side is a tert-butyl group on it. And so that's big and bulky. And so there's probably going to be less bromines coming to the back face, the front face of the molecule. So most of them will be in back. But again, I don't expect you to be able to predict that whatsoever. I just wanted to share the idea with you, is that you do form a pair of diastereomers. So you end up with this compound. So we'll put the bromine in the back. And then, of course, you have your methyl group going down here and your tert-butyl group coming up like this. So I'm just going to copy and paste this. So darn it. There we go. So copy. I'll paste it here. So we're going to get this compound and this compound. And these are diastereomers. So we'll put here diastereomers. But they're probably not going to be formed in an equal amount. And now that I've written that, it just made me realize that I forgot to say something on the second, the first reaction, and that is you'd get a pair of enantiomers. So we'll put here racemic for this one, okay, because there is a chiral center in the molecule right there. All right. So with that in mind, let's turn our attention to allylic halogenation, which is section 10.7. And I think that after this section, we'll take a short break. This section is not very long because you already know, let's say I gave you this molecule here. This is just cyclohexene. I'm sure you can all identify the weakest carbon-hydrogen bond, which is going to be this one, because if you break that carbon-hydrogen bond, you end up forming an allylic radical. Of course, the one in red is going to be the strongest bond because you form a vinylic radical. And then the one in green is somewhere in the middle. All right, so I don't think anybody struggles with that whatsoever. Maybe I could color code this just so put it in blue so we don't get any confusion here. All right, so now that you know that, let's talk about halogenating at an allylic position. So if you can abstract the hydrogen atom from the allylic position, yes, you form a resonance stabilized allylic radical, okay. And so if you were to take your cyclohexene, that's what's being shown down here, and treat it with bromine and light, you might think, okay, well, I'm going to get just strictly addition of bromine in the allylic position. I do the allylic bromination and I'm all good. You would get some of this product, but you guys know enough by now to know that if you have a double bond in bromine, right, you're also going to get, you're going to get some of this molecule. right? So you're going to get some of this guy where you get the anti-addition across that double bond. So this plus, it's an enantiomer. So how do you avoid getting those? Okay, so that's kind of the purpose of this section, is how we'll put here, avoid these, and then we'll put a question mark. How do you avoid those, right? Well, it's a great question. And the way that we do that is we use a little molecule called NBS, N-bromosuccinimide. So you remember succinic acid? Maybe you've seen that in biology or something, or succinate, right, which has 4 carbons. So N-bromosuccinimide has 1, 2, 3, 4 carbons in it. That's neither here nor there. But you see that if you take N-bromosuccinimide, where am I? I'm deleting too much stuff. And you heat that up, you end up producing a bromine radical. So what you're going to do is when you want to do an allylic bromination, you're going to treat the molecule, instead of with bromine, you're going to treat it with NBS, because it only makes a little bit of bromine in your reaction. Oh, sorry, a little bit of bromine radicals. And then what happens is that the bromine that you form ends up doing an ionic mechanism with the NBS to make some more HBr, because you need both of them to do the reaction. So let's take a look here. So first you do the formation of the radical, and then, like I said, the HBr, this reacts with NBS in an ionic mechanism, and they give you some bromine. So that's where this bromine comes from. This mechanism, by the way, is not covered in the textbook whatsoever. It's just mentioned briefly, so don't worry about it. But you produced only a little bit of bromine, a little bit of Br2, and so you form the new carbon bromine bond via a halogen abstraction, and that is how you do your allylic bromination. So overall, what do you have to do? You just treat the molecule with NBS, and that will brominate, but at the allylic position. And here's an example. Let's say we take this molecule here. You can see that we have an allylic position right here. But remember, the first step is a hydrogen abstraction. And so when you rip off this hydrogen in blue, you form this radical, and we see that that radical has a resonance contributor that we could draw like this. So we end up with 2 resonance contributors. And so the answer is, you can do the bromination at this position to form this compound, or you can do the bromination on the end to form this compound. You'll end up with a mixture. Now remember, this is not a carbocation rearrangement or anything like that. This is a resonance contributor, and that is why we get allylic bromination at 2 different positions. So with that in mind, it might seem like a lot of information, but let's just try taking a look at this practice problem here. Now, if I look at this molecule in B, the one I'm putting in the red box, it says predict the products when each of the following is treated with NBS and irradiated with UV light. So what we're going to do is we're going to take that molecule and we're going to treat it with N-bromosuccinimide, NBS, and we irradiate it with some light. So we're going to form a bromine radical, and it's going to abstract a proton. Now, in this molecule, there's only one allylic position, right? There's only one allylic position. And hopefully you can see that it's this position right here, the one that I have the blue proton, right? There's no protons on this carbon where I have the circle. And so that is where we're going to form our allylic radical. Now, if I draw the allylic radical, which is going to look something like this, okay? So I end up with something that looks like this. If I draw the resonance contributor of this molecule, do I get a different radical? Will it have a different identity, right? We could practice, if you can't identify it right away, you could say, let's draw a resonance contributor, which would look like this. So if I put this one in a red circle and I put this one in a green circle, is there any difference between the 2 radicals in the red circle and the green circle? Is there any difference between those whatsoever? No, they are identical. So since the second one looks prettier than the first one, I'm just going to erase all this. And we're going to say this is the intermediate that's formed. Okay, this is our intermediate. Oops, where's my blue pen? Like this. And remember, you form a little bit of bromine. And so that is where the bromination is going to occur. It's going to be right here. And there you go. That's the only product you're going to get. Now, the next one is a little bit trickier, isn't it? Right? Now, there's only one allylic position, and it's this position here. If you drew, let's say you took this proton in green and you drew one here. Well, those two protons are identical. The one in green and the one in red, they're the exact same, right? They're chemically equivalent. So I'm just going to remove that and say, okay, when we treat this with NBS and light, I'm going to end up with a radical, which is going to look like this. I'm going to stop doing that. Okay, which looks like this. So what we're going to do now is we're going to take a short break. I want you to draw the resonance contributor, and then I want you to draw the product of the bromination at both positions, okay, because there's two of them. And then I want you to determine, is there going to be a chiral center formed? Will you get a pair of enantiomers, et cetera, et cetera. So I want everybody to try to draw the second resonance contributor. I'll tell you, there is another one, okay, so we're going to have something here. I want you to try to draw the fishhook arrows, and then we'll draw the products of the bromination of both of those, okay, after our short break.